In this section, we shift from just storing data to actually organizing program logic. The focus is on functions, which help us write reusable pieces of code, and on modular programming, which helps us build larger systems in a structured way. This is an important step because as programs grow, we cannot keep writing everything in one long script. We need cleaner ways to separate tasks and reuse logic. By the end of this section, you should be able to define and use functions, pass inputs into them, return outputs from them, and understand the variable scope. You should also begin to see how functions work to form modular programs. Here, this slide is showing you how this connects to scalable systems as well, which is useful because these are not just abstract programming ideas, but actual tools for building real systems. This is to introduce you the motivation for functions. Without functions, the same logic gets repeated again and again. In this example, the code for calculating area is written 3 times with different values. That may look manageable in a tiny script, but in a real system, it becomes hard to maintain, hard to update, and easy to break through copy-paste mistakes. The function version helps solve that by defining the logic once and then reusing it. Why use functions? Here you can see the summary of the main advantages of functions. They let us write logic once and reuse it many times. They also make code easier to test because each function can be checked on its own. And in team settings, functions create clear interfaces where other people only need to know the inputs and outputs rather than the internal details. That is one of the reasons functions are so central to software development. Here is a real-life analogy, like a coffee machine. A function can be thought of as a machine that takes an input, performs a process, and produces an output. In the example, the coffee tap is the input, the brewing logic is the process, and the final drink is the output. This is like a simple mental model. A function is not just code, it is a system that transforms input into result. Now, what is a function? Here is the definition. So, a function can be defined as a reusable code block that performs a specific task and can be called from different parts of the program. This is important because it highlights 3 core ideas at once: reusability, single-purpose design, and the ability to invoke the function whenever needed. A function is basically a named package of logic. The benefits are expanded here into 4 main ideas: reusability, readability, maintainability, and testability. A well-named function makes a program easier to read because the name communicates the intention. It also makes updates easier since changing the logic in one place updates all uses of that function. And because each function can be checked separately, testing becomes more manageable. This is an important software concept, abstraction. A function hides internal complexity and presents a simple interface. In other words, users of the function do not need to know how it works internally. They only need to know what to pass in and what comes back out. This is one of the key ideas behind clean program design. This is just some idea to get you some practical examples, such as calculating total cost, validating user input, and pre-processing sensor data. These examples are useful because they show that functions are everywhere. A function is not just for math. It can also clean data, check conditions, or package domain-specific logic, so the rest of the program stays readable. This is the central design principle of this section. Functions allow us to decompose a large problem into smaller, manageable components. Instead of thinking about the whole system at once, we split it into tasks, solve each task in a function, and then connect them. This approach makes complex programs much easier to understand and build. Here is the introduction of the structure of function definition. It starts with the keyword def, followed by the function name, then the parentheses for parameters, a colon, and an indented body. If the function sends a result back, it uses return. So remember about indentation. It's important in Python because indentation is not just style. It defines the code belongs inside the function. This is like a simple example of a function, the function greet. This is defined, and inside it, there is a print statement. But here's an important point, because defining a function does not execute it. At this stage, Python has only learned the recipe. It has not yet run the recipe. Here is how you can run the function call. Writing greet with a parenthesis tells Python to execute the function body. This is an important distinction, as the function name by itself refers to the function, but the parentheses are what triggers the execution. This will connect the definition and the call to an actual terminal output. The program prints hello, only because greet was called here. So you can see the full chain. So you first define the function, and then you say what it should do, and then you call the function, and then only you can see the output. So this is just to reinforce what you just learned. A function definition is like creating the recipe or blueprint. The actual work only happens when we invoke it. Many beginners might expect code inside a function to run automatically once it's written, so you have to understand that it must be called to be executed. Parameters. So what are parameters? Parameters are introduced as inputs for functions. They allow a function to work with different values instead of one hard-coded case. Inside the function, parameters behave like local variables that temporarily hold the values passed in. This is what makes functions flexible and reusable. Here, with the same greet function, we are now having a parameter called name. It acts as a placeholder, so the function can greet different people depending on what argument is passed in later. This is the bridge from the fixed behavior to dynamic behavior. Here, we are putting a different parameter. So now we are calling the function and putting the argument in the quotation as Ali. So now when you call this function again, it's going to just show the output as hello, Ali. The output hello, Ali is just what I explained in the previous slide. It confirms how the parameter mechanism worked. So the value passed into the call, Ali goes here, and then it gets executed. So when it's being printed, it's taking the argument that you just passed in. This is to summarize the whole point of parameters. Without them, functions are rigid and tied to hard-coded values. With them, the same logic can handle many different inputs. That flexibility is one of the biggest reasons functions are useful in programming. This slide is to show you to show you what happened between print and the return. So printing only displays something on the screen, but the value is not handed back for use. Returning sends the value back to the caller so it can be stored, combined, and used in further logic. So this difference is essential for writing meaningful functions. As you can see here, they are just printing the result. So that would be the output. But here, it's going to return it. So return A plus B is going to have the updated value. explaining more in details. So the function add a, b, returns a plus b. So here you can see that the return would send that data back, and it also immediately ends the function's execution. So it's important to remember that once Python reaches a return statement, it exits the function. This is to show you how a return value can be captured in a variable. The result equals add 2, 3 means the value produced by the function is stored and can be used later. This is what makes return values far more powerful than simple printing. The output confirms that add 2, 3 evaluates to 5, and that value is what gets printed. It is to reinforce the evaluation process. The function call is completed first, and when the function call is computed, the result is stored, and then the variable is printed. Return values allow chaining and composition. A function does not have to be the final step. It can produce the data that becomes the input to another part of the program. That is how small functions start combining into bigger systems. Now let's discuss multiple inputs. How do functions take more than one parameter? Multiple parameters allow the function to capture richer behavior and work with more complex situations. Note that parameters are separated by commas and matched positionally when the function is called. Here's a simple example. This calculate area, this function, is having the parameters length and width. It's very straightforward and also useful. So this function is taking two related inputs and combine them logically. This keeps the interface clear, so one input for length and one for width. Now we are passing the arguments here. So here there is this print and we are calling the function, and you're putting the values 5 and 3. So the order matters here. So the first 5 will go to length and the second number is going to go for width. And if the order changes, the meaning may change too. The terminal output confirms that the function returns 15. This is a useful example because it is simple enough to follow, but it also reinforces what the parameters and return values and function execution can do at once. This is just to broaden the idea, like calculation, data processing, and sensor fusion. It shows that functions are not just classroom examples. They're used to package logic for transformation, analytics, and combining multiple data sources in practical programs. Now I will be introducing you to variable scope, which is one of the first tricky ideas you may meet in functions. A local variable exists only inside a function and disappears when the function finishes. A global variable is defined outside functions and remains available across the program. Local scope provides isolation, which helps prevent naming conflicts. So this example is using the same variable name x, both globally and locally. This is a good example because it is going to show you that two variables are separate despite sharing the same name, which is x. The local one belongs only to the function with this indentate feature, and the global one is outside the function. So the output for this print x, I'm going to show you in the next slide. The output is 10 for the global variable, and 5 for the local variable. When test runs, it prints the local x, because this x is equals to 5 is defined within that function. But when the print x is called outside the function, it will print the global variable, which is 10. This is to reinforce the idea of shadowing. So a local variable can temporarily shadow a global variable with the same name inside the function. That does not mean the global variable has changed. It only means the local name takes priority while the function is running. Now we will introduce default parameters, which provide fallback values when no argument is passed. This is useful because it makes the functions easier to call in common cases while still allowing customization when needed. It is a nice balance between flexibility and convenience. So now we are going to use our same greet function. At this moment, we are having this greet function, but now we are having a fallback value and putting it as guest. So this shows how a default parameter works. If the caller does not provide a name, the function automatically uses guest. This makes the function more robust and beginner-friendly as well, because it can still run even when no input is provided. This is to compare two calls, greet without any input and greet with the input Alice. So you can see that when these two will be called, the output will be different, because when the greet is just called on its own, it is printing out the default value, which is the guest. Now it is about the docstrings, what and why. So docstrings, as in code documentation, are placed immediately after a function definition. Their role is to explain the function's purpose, so the expected parameters as well, and what the values may return. This matters because code is not just for computers. It must also be understandable to other people and to our future selves. Here is an example of docstring. This explains how to do it. So first there will be the function definition, and then we follow the style of writing and explain what this function is doing and what it will return. So it is explaining returns sum of two numbers. And remember the indentation, it is placed immediately after the definition line and describes the function's purpose. So why do docstrings matter? They improve readability, help collaboration, and support tools like help and IDE tooltips. In other words, docstrings turn a raw function into something easier to understand and reuse. This is particularly important in teamwork and also big projects. Now let's focus on modular programming. What is it? Modular programming means breaking a large program into smaller functions and separate files. It helps organize related logic, improves clarity, and makes the code reusable across projects. This is a major step from simple scripting toward proper software design. This one highlights the benefits of modular programming. It's easier debugging, reusability, and separation of concerns. Separation of concerns is especially important. User interface code should not be mixed with calculation logic or database logic. Keeping this separate makes the system easier to understand and maintain. This introduces you to the import keyword. So import keyword is being done in this example using math module. So by importing math, we gain access to functions like math.square and then we are putting the value 16. So see the dot notation. which is how we access the functions inside that module. So square root is a function inside that module math. This is like the first practical step in using code written elsewhere. The output 4.0, the float, confirms that square root returns a float. This is a nice simple example because it shows both how importing works and how a standard library function can be called directly once the module is loaded. This is an example of an applied application slide. So it builds a small pipeline with 3 functions. One gets temperature, one calculates energy, and one controls the system based on the energy value. The flow is clear, so sensor input then becomes processed data, which then becomes a controlled decision. The final output is cooling on because the temperature of 28 produces the energy of 280, which is greater than 250. This is an excellent example of how separate functions can work together like system components. So what is refactoring? Refactoring is introduced as improving the internal structure of code without changing what the user sees. That means the outputs stay the same, but the code becomes cleaner, more readable, and easier to maintain. This is an important professional habit because software rarely stays in its first draft form. Here's the before and after. So here's a comparison of repeated even checking code with a function-based version. The before version duplicates logic and mixes checking with output. The after version wraps the repeated logic inside a reusable function. Here you can see the check even is being called and you are not doing it how you did it in the before version. You can see what refactoring looks like in practice and not just theory. Here the function became cleaner. The check even n now returns a Boolean result instead of printing directly. This is a stronger design because it separates logic from presentation. The function answers a question and the caller decides what to do with that answer. The benefits of refactoring. So it has cleaner code, more reusable code, and maintainability. Refactoring reduces redundancy and makes future updates safer because the changes happen in one place instead of many scattered locations. This is to pull together the major ideas. Functions provide organization and reduce duplication. Parameters and returns manage data flow. And variable scope controls visibility to avoid conflicts. This is a useful checkpoint for you because it links syntax, logic, and software design into one picture. This is to reframe the section as skills development for you. So you're not just learning what functions are, you're learning how to define them, call them correctly, manage return data, use defaults and docstrings, and combine functions into larger systems. This is a strong shift from isolated coding tricks to actual programming practice. The key message here is that functions are building blocks, just as components in an energy grid working together to form a complete system. Functions combine to create larger applications. You can see that functions as a part of a coordinated system rather than standalone fragments. What's coming next? So next section will be on file handling and advanced topics. The transition is so you see how to organize code into functions and modules, and then the next step to connect programs to the outside world through files, persistent data, and error handling. This is a reminder and some action items. So you are encouraged to convert repeated code into functions, add parameters, use return values instead of only printing, and write docstrings, and organize related functions into a module. The bonus challenge is that if you can expand that case of that energy system micro case, which is a nice way you can connect the section back to a somewhat realistic application.